Okay, so these are questions number 4 and also question number 5 of the magnetic fields homework booklet. So in question number 4, we've got a wire and it lies perpendicularly across a horizontal uniform magnetic field. So your magnetic field is going in this direction, and perpendicular to that, you've got this wire here. And the magnetic field is uniform and it's got a flux density of 20 times 10 to the minus 3 Tesla. And 0.30 meters of the wire are subjected to this field inside these magnets. So if the force exerted on the length of the wire is 30 times 10 to the minus 3 newtons downwards, we need to know the current in the wire. So basically what we do is we take our equation, F equals BIL, and we want to know what the current is, so we want to know what I is. If we rearrange the equation, we simply get this, and then we just put our numbers in. So F is the force, which is the 30 times 10 to the minus 3. The magnetic flux density is B, so that's 20 times 10 to the minus 3, and the length of the wire is 0.30 meters. And if we do that, we basically get 5 amps. So therefore the answer is either C or D. We now need to try and work out whether the current goes from P to Q or Q to P, and to do that we have to use Fleming's left-hand rule. So we point our first finger from north to south, so that goes along there. We know that the force is going basically the force is a downward force, so you point your thumb downwards, so you rotate your hand around so it's pointing downwards, and so therefore your second finger, which is the current, is basically going into the paper. So in other words, it's going in this direction, so it goes from Q to P. So therefore the answer is D. For question number 5, what we have a horizontal straight wire. Again, it's got the same length actually, it's got a length of 0.30 meters, and this time it's carrying a current of 2.0 amps. And again, it's perpendicular to this horizontal uniform magnetic field. And again, we know the flux density. This time, though, the wire is floating in equilibrium in the field. So what this tells us, because it's in equilibrium, is that the resultant force vertically is 0. In other words, the weight downwards is equal to the magnetic force upwards. We want to know the mass of the wire. So if we think about it, this is our equation for a conductor in a magnetic field, and this is the weight of the wire, and they're equal to each other. So if we simply rearrange this, we get the mass is equal to this equation here, and again we just need to put our numbers in. So this is the magnetic flux density of 5 times 10 to the minus 2 Tesla. I is the current, so 2.0 amps. L is the length of our wire, 0.30 meters, so that's 0.3, and G is the acceleration due to gravity. And if we do that on our calculator, the answer is 3.1 times 10 to the minus 3 kilograms, and so therefore the answer is B.